Thank, thank you for surviving to the last conference. We have Bernardo Uribe. He's a professor in Universidad del Norte. Also, is member of the scientific committee INSA. INSA. Institute of Mathematics here in Miami. He did his career, his mathematical career in Universidad de Andes, Bogotá, and then he did his PhD in University of Wisconsin, Madison. He's member of the Academy of Science in Colombia. The reason that we are here.
Well, thank you, Rafael. Thank you all for staying last talk. So, I came to the subject because of Rafael some years ago, and in the thinking, in the trying to do some input into this physically interesting questions, and I stumbled to distinguish what is a topological invariant of specific symmetry, and the specific symmetry, it is this what Higinio mentioned. So I'm going to put it here below, and I'm going to put it here as C4, and I'm going to put some decorations. So the question that I had to answer, and I'll explain all these decorations what it is. This is not Sol, but Soc. I had to find out whether system with a C2 with a C4T symmetry with spin orbital coupling and had an invariant or not. And the invariant was quote easier to calculate with a specific Hamiltonian of the device, but I wasn't sure that this invariant was topologically invariant. But you can cook up a number, but you don't know if this number is stable or this number is just the log key, and you got it. So then I had to calculate this because I knew from what I was doing with Rafael that I had to work in these K-theory groups. And I somehow know how to calculate these things because if we have all the structure of the algebraic topology like that, you have a cohomology theory, that's equivariant, and all these things, there is a way to decompose the space in pieces, as Tom was saying and Higinio was saying. And then you can just build this Lego of pieces and try to detect what is this. But when I was trying to do that, I found out that I myself could not find in the literature or anywhere the structural pieces of this thing. So the structural pieces under algebraic topology would call it what is the spectrum of the homology theory. But let's forget about the spectrum. What is so this is a magnetic group here. And so the question is, what are the K theories of a point? Because you have the homology of a point, then you start gluing it with some procedures called manual ligatory sequence or other things that you learn in algebraic topology, and you cook it up from the bottom up. Of course, there is the suspension functors that Professor was mentioning, and they say topology is easy because you know something and then you do the rest, but the structural piece is this. And this is what Higinio was trying to tell us yesterday about this structural piece, that is the spectrum. But then I also stumbled upon the decorations, these decorations that go here on top, that Tom mentioned, which are the twistings. So these decorations are very important because the twistings are precisely that is underlying many topological obstructions. So the twistings in cohomology is orientation, it's Tito Witten class. So that has to be there for any cohomology theory to be complete. You have the twistings because you want to do something that is called the Thom isomorphism, and you need to know whether it's orientable or not. If it's not orientable, then you get a twist. K theory has more obstructions for orientability. Not only you need it to be oriented, you also need to be spin C. So that's another one that is the integral class of the Stigall-Witten. So that means that there are decorations that are there that are disguised as sock or things, but in another perspective are called obstructions for the rotation of K theory. So since I stumbled on that, I wanted to see how do I organize these twistings. And these twistings have been organized in other perspectives by people in the 1960s when index theory was very important, but it was not organized in the set of magnetic groups. So I went to see how do I organize it. And of course, what lies behind it is this very well quotes known tenfold way. When they say quotes, because there are many interpretations of the same table, and each interpretation can be read as some information that you like or some information that you dislike. And so I decided to put what I'm going to exploit, which is something called the graded Brauer. Brauer graded group, but it doesn't matter. So the graded Brauer group, which is what goes here on the left, that I'll explain in a second what it is, but the point is that there are the graded Brauer group of the field, which is the reals, or the field here is complex numbers, and these are the generators or the representatives of the classes. You could take the Clifford algebras. Clifford are very well behaved because you can tensor them. And from here you can go here to here, and then they have this periodicity that is the eightfold periodicity. But a very nice theorem of Wedderburn tells us that all these ones have a structural piece, which is a division algebra. Every matrix algebra, in some sense in this case, every algebra of this type is a matrix algebra over a division algebra. And so the division algebras are here. These are, you could cook them up from the Clifford algebras. Of course, they are inside, like the quaternions lie here inside, and the other part you can take it out because of its equivalence. So these are like the smallest pieces that you can from this cook this one. And then you see complex numbers, quaternionic numbers. But then the way in which the Altland-Zimbauer structure is built is through the complex numbers and conjugation. And so then I did this middle term, which is what I'm going to talk about here, which is instead of talking about modules over the reals, I will talk about modules over the complex numbers together with conjugation. So in some sense, the algebra people would say, I have the field and the Galois group. So I have the field, the Galois extension, and the Galois. So it's all there embedded. But then instead of looking at it this way, I complexify, but then I change bases. Then so I say I complexify this Clifford algebra, I change bases, and then it looks like this. In this new base, it looks very nice. It looks like matrix algebra. This M2 means matrix algebra, by the way. And if I see 1, 1, it's a matrix algebra, but on which we have vector space of degree 0 and vector space of degree 1. So it's a graded vector space, and this means the matrix algebra of a graded vector space. So, and as you can see, these models are very small, also coming from that one. And then you can see how you build the CPT symmetries, knowing these gadgets on the middle that come from the gadgets in the left. So in this way, that's why I gave you this handout, because if one sees the way it's presented, sometimes it's not clear why do I present it this way. But if I have this middle term in here, that is kind of structural because it has more structure than these like isolated pieces, then I could see what is the algebra behind. And somehow if I do change of basis, boop, I end up in the Clifford algebra. So this information, once here, I notice what I have to do is, if I want to understand all these 10 options, if I have a group, this is the way I can expand it. So I change the group and I think about what is here. What is there? Something called graded, simple, central algebras together with automorphisms of a group. And this is what is being classified in the middle column. So, and this tenfold way could be better understood in my thought about these options here, which are modeling certain specific algebras with symmetries. The good thing about this middle term is that it's a group. This is a group of order 8. That means if I take this algebra and tensor it with this algebra, I get 2 plus 3, 5. So I can tensor them. If I see it, of course I could tensor them if I see it like this, but then I have to disguise this because I need to know the algebras where I'm talking to. So in that sense, I could imagine instead of having this disorganized table that I could think of it as 1 minus 1, 1, 0 minus 1. I could think it's better this way. There's a generator, I generate everybody, and it becomes a group. That helps a lot. So the point is that I'm going to explain you how to get into this idea. So for that, that's why I gave you a handout. But I want to tell you 2 things before, some funny things. We had the beautiful experience of receiving the review of this paper today. It was beautifully rejected. And so I copied a sentence from my beautiful review of rejection that we got this morning. because in some point we explain how to go from here to here, from here to here. So the beautiful referee says the physics discourse, page 10, blah blah, should be clearly stated as non-mathematical part excursion into physics. It is not any proof or fact, but it's rather like an analogy. So this is from the rejection of this paper today, exactly. So now they were like waiting for me to give the talk to reject the paper. And which Journal of Pure and Applied Algebra. And there was no reason for the rejection. Simply that the A was used twice, that there is an error of the sign, and then it's not fitted for publication in the journal. Anyway, so I'm old. I have a crocodile skin. I don't care anymore, but I found.
Es lo que es para los huevos.
Let me show you my excursion into physics. And yesterday, the student is not here. The student that is here, that came last year from the university, asked me in my face, Professor, when will you do mathematics again? I said, what? Going to his head. I'm not doing mathematics, and I don't know what I'm doing. Anyway, so it's terrible. It's very encouraging. So the whole point is that we need to first set up our fields. Of course, we are with the reals or the complex numbers, and we know this is the Galois, complete Galois extension of that one. And one of the complaints of the reviewer was, why don't you do it with the complex numbers? You do it in any field, and any field extension, and the Galois group. Then, of course, things are more difficult, and then we don't get anything out of it. So we want to understand, or let me give you the definition, what is a graded, simple, central algebra over a field. So I will be looking at rings, fields, a little easier. So we have, our field will be this, any of this. So I think it's the complex numbers of the real numbers. So we want algebras over this, so we need algebras over K. So think of your matrix algebras. And so what first graded? So graded will mean here in this universe super, no? Super algebra, or Z2 graded. That means that my algebra is split into two pieces. Namely, two vector spaces, one is degree 0, the other one is degree 1, degree 1 squared equals degree 0, as we know from these variables. So simple. Simple will mean that it has no trivial two-sided ideals. So if you think of it, that if you have a non-trivial element, it will generate the whole lot, like multiplications and sums, and so this is no trivial two-sided ideas. So if you think of it as a whole block, you take anything and then you just do all the multiplications and sums, you can generate that. Central, and this is also key part. Central means that the center, so namely the people that commute with everybody of the algebra, has to be the field. And I put graded center. This hat stands for graded, because of course we need to use everything using the Kosul notation or change of variables. When they're odd, you need to know that the variables are odd, and you flip them, they get a negative sign in front. If not, they get a positive. So all these things together is what we want to study. Graded, simple, central algebras over the field K. Of course, we divide by isomorphisms of algebras, but then we go one step further, and we want to say that two of those algebras are going to be similar or equivalent classes if there exist two vector spaces or two vector spaces in this field, such that, and this is the Morita equivalence, such that when I tensor them, of course, this is a graded tensor of endomorphisms, they become isomorphic. So I divide by this equivalence relation, and what I get, so with this equivalence relation, I get, and I put it here, graded, simple, central algebras up to this Morita equivalence, and this is going to call the graded Brauer group of my field. Okay, this is the definition of algebra. So in these cases, there are few of them, and then the good thing is that what are the answers? So how many graded Brauer how many algebras of this kind are over the complex numbers. So there are only two, because the only ones that matters is either it's a matrix algebra, because any algebra of complex numbers that is created at the central single level is a matrix algebra, or you have an element of degree 1 that is outside. And what is the graded Brauer group of the reals? It is Z8. I didn't say it, but this object here comes endowed with a tensor product. So it's a monoid, but this object becomes a group. It's not only a set, it is a group, and this is very important, and this is what we want to exploit. It becomes a group because you could have two of these algebras, tensor them, you get a new algebra, and it's one of these kinds. Products, tensor product of central algebra is central, it's still simple, and it stays in the category. So then this whole thing is a group, and that's why I'm writing here groups. Now,
how the inverse? I don't understand the inverse.
well, the inverse, you need to use this equivalence relation.
Those modules, they need to be graded.
Everything is graded. Everything exists, graded vector C2 graded vector spaces, or modules over K, T2 graded modules. You're right. So I am allowed to put in here graded vector space. So the equivalence relation is modeling out by those.
And the opposite algebra.
Yeah, the opposite algebra works in this place because then you just tensor and then you get endomorphisms.
Okay.
But you're right. So this is the inverse. So the opposite. But here we could simply imagine that this is generated by the Clifford algebra over the complex numbers, and here is generated by the either this one or the other one over the reals. So the Clifford algebras are nice generators of these graded Brauer groups, and of course we have to know some relations of the. So what do I mean by this object CPQ? Well, we need to think that this is D is generated by some variables to the plus Q that they anti-commute, and that EI squared equals 1 if it's less or equal than B, and is minus 1 if I is bigger than B. So these are my Clifford algebras. We know how to use them. If it's over the complex numbers, it doesn't matter, because we can do a change of variable, and then you can put either all positive, all negative, it really doesn't matter. But the point is that with these Clifford algebras in mentioned, you could use the nice properties of the Clifford algebras, and then they add. And then this is structurally important. They add the coefficients. And so I'm not using the notation of Atilla and Box because they used them backwards, but this backwards thing is very complicated to keep. I'm using that this is kind of the reals and it's the imaginary part. But you can do this, but what is more important is that if you go, and then who said, I think Professor Loring was the one saying, you need to calculate something at some point. It's not just moving letters, so you have to calculate something. And so then this becomes the endomorphisms of r to the 16 in degree 0 plus r to the 16 in degree 1. So then this gives you the periodicity. This is the periodicity of what? Namely, you just go and do, and at some point you reach your equivalence class. And so then that's why it's a period, because this is a matrix algebra. So somehow one can try to learn about this through other methods, and it's like very difficult, but algebraically it's quite simple. So because of this, then Clifford algebras are very important because there are some sort of generators of certain specific type of algebras, and these algebras are the ones that are behind the KT. These are the algebras acting on the objects that we want to classify. When we do it in condensed matter physics, we know because we have the operators that generate the algebra were there, like time reversals with a matrix, or they are the objects generating the algebras. So it's just somehow, sometimes we don't need that many operators, just perhaps one, and then the rest is behind the story. Good, so then in this table that I showed you, there is something that was called graded division algebra. So what is a graded division algebra? So of course, over my field, no, over my field K. And well, this is any algebra. It's a division algebra if all elements are invertible besides the zero. These are algebras on which all elements are invertible, such that all elements besides zero are invertible. Not zero are invertible. Okay, how many of them are they? And this is the tenfold way seen as division algebras. So if we forget about the grading, somehow the ungraded ones, the ungraded, over the reals, this is what is called the Brauer group over the reals. And we only have three. This is the reals, not two. The ungraded over the reals is, yeah, the two, sorry, two. The Brauer, yeah, and the quaternions, because the complex not there. And the ungraded over the complex is just the complex numbers. So these are the ungraded division algebras. So these are three, and we still have, we need 7. So the graded ones, well, you can imagine you take an ungraded and you start putting things to make it graded. So we can take the reals and put an element, and we can divide by e squared equals plus minus 1, or we can take the quaternions and put an element and divide e squared plus minus 1. These are already 4. And then we have the complex numbers, and we can have an element, and we could either divide, we could divide by this ideal, and then we could either choose that it commutes with I, or we could say that it doesn't commute with I. So this is the anti-unitary ones in some sense. Or we could simply divide by this, and then we say that they commute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the division algebras. This is all that there is, and this is somehow the structural pieces. Or if you're just wanting elements to be invertible. But why is this important? Because there is a very famous theorem of Wedderburn that tells you that any graded central simple division algebra is a matrix algebra over a division algebra. Right. Again, I'm working over fields so that I don't have to worry about problems with rings. So this is a theorem that is, we can only get one theorem today, is this one. This is Wedderburn, Artin. And it says that if A is a graded central simple algebra over my field K, then it is a matrix algebra over a division algebra. So A is isomorphic to a matrix algebra. This M means matrix algebra of degree then of B, for D is a graded division algebra. So behind it, that it means that, okay, if you want to understand central simple graded algebras, it is understanding graded division algebras, because anything that you put here, you can do this as a change of base. So that means is anything that you put of these 3 algebras, they could be reorganized as matrix algebras of these 7 small pieces of objects. So these are the tenfold way as division algebras, and they could be seen as representative of the classes, which are these Clifford algebras that don't look like matrix algebras of a division algebra, because that's a change of base. So it gives you a presentation of Clifford algebras, but it could also be presented after non-trivial base, change base, it could be like this. So but these ones cannot be tensored. The tensor division algebras is not a division algebra anymore, but the Clifford models could be tensored. So depending on which vision do you want to take, then you could use it in your perspective. So this is one of the columns, the division algebras. But there is, of course, the other column that the people in condensed matters know about them. But if not, so it's this CPT types of symmetries. We have a Hamiltonian, and we say that we have the symmetry or not the symmetry. This is the time reversal operator, whether after some things in the middle, which I'm not going to write. This is the time reversal preserve, time reversal. And if we have the particle Hall symmetry, then we do it like this. But then I will tell you what is the C2 grading. And if we compose these two, this is the Carroll symmetry minus H. This is chiral. And this is the chart conjugation symmetry. On what is here what is here what? So we have to think that the Hamiltonian is giving me some eigenstates, and I will take the ones below the Fermi level. Let me suppose that they have a gap. So because this preserves the Hamiltonian, then the time reversal is acting on those eigenstates that are below the Fermi level. So the module obtained by the valence states is going to be a module of this thing, but because it's a conjugation, there are two options. In this conjugation, you either have plus or minus 1. But conjugating, you don't notice this because it's on the center. So this is on the center, you don't see it. But the symmetry that is actually happening is this one. This is how you lift it to be a symmetry of the matrices. Here, what's going on in this one? The same happens here, but this is a degree 1 operator because it's flipping the valence states to the conduction states. Conduction states to the valence states. So this is a degree 1. And this is a composition of these two. And in this one, square equals 1, or you can change your base so that it looks differently. But the thing is that these two are anti-unitary. It's anti-unitary. Meanwhile, this one is unitary. And we could think that this one is the composition of these two, but let's suppose that is like that, so that we don't have to work. And this one is also degree 1. And in the table that I showed you is to organize this information into this same information or into this same information. Changes of bases, non-trivial in some senses, and you choose which universe you want to live in. So I was telling some of the other people, if you see this structure here, it's difficult to cook up a group structure. But if you see it here, the group structure is natural, it's completely natural. So one perhaps would change your bases, put it here, and see that there's an extra structure on this object. Here you don't see it. So in the classification that is usually given, you have some sort of Z2 cross Z2. Either you choose time reversal is on, or charge point reversal symmetry is on, or the diagonal is on, in all these numbers. And one might think that the appropriate group is C2 plus Z2. It's not the appropriate object. The appropriate object is C8, which is the one that is here. This is just some sort of classification that is classifying other type of structure. Let me tell you now what is the next step then? How do I make this more interesting, or how do I put any group now? And if one goes to the world of algebras, then one knows what to do. And so perhaps if one is coming from topology, then it's not clear. But if you go to the world of algebra, then it's easy to do. You know what to do. So let's put what we want to. I want to define the magnetic equivariant graded Brauer group. So I have told you what is the graded Brauer group. Now I need to put a group, and magnetic simply means what Inyo was saying. So what is my input? And of course, G is my group, and it could be anything until I need to be something. Any group, being non-compact, whatever. But if I want some structure or some simplicity, then I put that is compact. So this is the magnetic group, which actually is just telling me which elements will act complex linear, which elements will act anti-complex linear. Let us recall that if V over the complex number is a magnetic representation, if, of course, G is acting linearly, the reals, that is complex in some part and anti-complex, if G acts on B, but let me call it that the kernel of this phi is called G naught, as Kinyo said. If G acts is linear, C linear on V, if phi of G is equal to 0, and if G acts antilinearly, if you don't know what that is, that means simply, in this case, that if I have G acting on, and this is a complex number, and this is a vector, antilinearly means that comes conjugate, and the action is like this. So instead of having that I can take out the element when it's in the field, I need it to conjugate. That means antilinear, so it flips the object. So lambda here belongs to G. Now this is a representation. Good. So now what are the magnetic, equivariant? So I want to put magnetic, equivariant, central, graded, central, simple, all these things, algebras, because this is what I'm going to study. So all these decorations, magnetic, is simply we start with a central, simple, graded algebra, and we want a group to act in it. So we start with a central, simple, graded algebra, or graded central, simple. They all commute over this are the complex numbers. And we need to put an extra structure. The extra structure will come from automorphisms of the algebra. So I have this is the first thing I need to have. And secondly, I need to have tau, which is the action of the group into the algebra. So it's going to be a group homomorphism to where? Luckily, Eugenio said yesterday the word, so I need automorphisms of this. But I'm going to put the word M, or the letter M, in front. Automorphisms of graded algebras. So I'm going to allow the automorphisms to be linear or antilinear. That's all. That's the only extra thing I do. So the automorphisms here it could be linear or antilinear, no? C linear or C antilinear. To capture this information. And this is my information of what is going to be a magnetic graded central simple algebras. And we actually do the same game as before. And we say that A comma tau, yes?
They need to commute the grade.
Yes. No. No. You see, I will use a beautiful theorem of Noether, Colin Noether, that says that any automorphism for graded central simple algebra is inner. So I don't have to worry. But it's not me, no. These are these beautiful theorems that tell you that everything is as easy as possible. It's just amazing. Because Emil is correct. I haven't said that it has to be of degree 0, but it will be of degree 0 because you will get conjugation. But that's theory. That's if I put any other algebra, might not be. So Wedderborn first, then Skolem or Skolem Noether, and then we can use now the result. But what we do then, we actually take all these objects, so we call it graded, equivariant, magnetic, central, simple algebras, which means an algebra with this information. And of course, what we want to do is we want to say, I want to say when are those two of those equivalent? And the same thing is the Morita equivalence. But the Morita equivalence is if there exist two representations, magnetic representation. If exists V and W, magnetic representation, namely that that's completely linear part, complex antilinear of the other part of this G, 5. And the same thing as before, such as A tensor, the homomorphisms of the first, is isomorphic, to A prime tensor, then the homomorphisms of the second. And the action is given by the inner product given by this thing, because we have a representation. Namely, if we make it to be similar to a representation, it's trivial. It's a representation of the group. But because we have automorphisms, these are conjugations, so we have some central parts that I'll explain in a second. And then if we do this, then we define what is the graded Brauer group of G, 5 with respect to the complex numbers is all these algebras. So magnetic, graded, central, simple, algebras over C, equivariant, G, 5 equivariant, divided this equivalence relation. Again,
equivalent depends on phi. So
Yeah, phi is somehow embedded into this structure. There is a g comma phi. I should have said it. And then here, of course, there is also a map that has the conjugations to C2, and it has to be equivariant with respect to this phi.
the equivalent relation would be correct with the phi. And find
Yeah, you're right. I'm not completely explicit here, but everything has to be compatible, and of course, this has to be G equivariant. This has to be an isomorphism that's G equivariant. G is acting here. G acts here by conjugation. G acts here, and G acts here by conjugation. So if you get an isomorphism that is G equivariant, then they're going to be similar. And of course, so the conjugation is going on in the action here and the action here. That's where the
and phi will tell us if it's linear or anti-linear.
yeah, phi tells us when it's linear or anti-linear, and of course, when I do this, it's because I know whether it's linear or anti-linear. Having said this, then this has a tensor product. It works equally as in the non-equivalent sense. You just take the diagonal action, I put it here, G diagonal. And therefore, this becomes a group. And I want to tell you what is this group. And the point is that this group is all the twists that Tom was saying. This group contains all the twists in an organized manner. So let me somehow give you the answer, and then if we do this, we are simply done. So if you want to, of course, this is just over a point. So this is just, I said, it's over a point. I don't have a space anywhere. This is just what's going on over a point. And if I want to have some certain symmetry with certain structure, then I need to figure out what is the central simple algebra they have and how is this group acting by automorphisms. But let me just then bring this result that is very important. So this is the theorem of Skolem Nether. Supposedly to be done first by him and then by Emmy. But so it says that automorphisms of course, at the time, they were not caring about graded algebras, but it could be generalized to graded. So I'm going to put it here in graded, meaning C2 or super. Central simple algebras. And this is again over my field, not over a ring, because I need to put extra thing, are all inner. So that means that any automorphism that I can cook up, it was a conjugation. That already makes it simpler. So that means that if I have such an automorphism, that is acting on my algebra, doesn't have to square to 1, it just have to be an automorphism. That means that this tau is the adjoint of a matrix, or not an adjoint of an element in the algebra. Adjoint of an element in the algebra. So where M belongs to the algebra. So that means anything that you can imagine that you were doing here at the end is just a conjugation, and this we know from the automorphisms of the matrix algebra. Any automorphism of matrix algebra is a conjugation. It's a change of variables. And the center that is going on. So this is a generalization of that theorem that simply allows us then to, whenever we have an automorphism, we go and pick who is the representative of the conjugation. But when we choose a conjugation, there is a central element that we don't know what it is. And this is the choice of t squared equals 1 or t squared equals minus 1. So we don't know the center. We don't know what else can we do with the center. So good. So having this in mind, we can and I haven't said it, but if we want to put complex conjugation, we can simply put complex conjugation at the end. Because you have an automorphism that is not linear, then you can conjugate, and you get an automorphism that is linear, so you can actually put here the conjugation. But with this is enough, no? This theorem is what is important. If you want to make it antilinear, you put conjugation. So having this in mind, then let us state That's the result that we finished already. So then this is our result, and of course it generalizes many well-known results. No, this is I'm not claiming that I invented this because this is just building on results of all others. So if I have a finite, let me put it like here, so it's here finite magnetic group. So what is the graded Brauer equivariant with respect to this of the complex number? Note that the group is not graded as Tom was saying. There's an extra grading that I want to see that is actually acting with the degree 1 automorphism is just simply flat. So far it's flat, but the extra automorphism will become twist. So what is this? This is isomorphic to the following, and I'll write the whole. So we have central extensions, but of course the central extensions have to take into account that phi controls whether the group is acting by conjugation or not. This is just a declaration to control central extensions, but are magnetic central extensions. So this is the part of magnetic central extension. As Hino was saying, so we have some sort of group here, we have group here, and then we have some C star. And then again, it has to be compatible with the magnetic part. So these are magnetic central extensions of the group here. This is what here stands for this. Then we have, it's not a semi-direct product, it's an extension by the group of homomorphisms. This is the first Stiefel-Whitney class, in some sense, in some universe. So it's not the product of groups, there is a cocycle that tells you how to go, so to multiply things from here that go to here. And there is another cocycle here that goes to Z2. So this is a group. It's difficult to see it this way because this thing could be Z2 cross Z2, and at the end is C4. And I'll give you an example of this because the most famous one is the project. So this is the theorem, and then we can see, for the ones that know old-fashioned things in topology, this is basically saying, well, I'll tell you what, but this is related to, this is the first Stiefel-Whitney class. If you put a space, and here is the integral second Stiefel-Whitney class. The spin C obstruction. But there's no topology.
Not related to the GCM to the invariant.
Yes, it is. If I were to put a space, yes.
Okay.
But so far I have a group and there's a point, so I don't have a space yet. But if I were to put a space, then I would, among the many twistings, I will have that class. There are more. No? Good. So we're trying to convince you that this is a theorem that that was done by CTC Wall in the 60s. So you see, I'm only telling you things from the 60s or 50s. This is like, I was thinking, this is like knowledge is periodic. It appears again and it disappears, and so just
only 60 years, 3,000 years.
no, of course, but at least this wasn't done before. So this starts and then it's periodic, appears. So we are in the second time that it appears, or third time that it appears cyclically. And so this theorem is the classification for the simplest case, of course. C2 is my group, and this is the identity. So this is my phi. So the simplest of the simplest of the simplest. This was done by CTC Ward. He didn't do it in the complex number, he did it in the reals, but it's the same. So in this case, I put it here. And then what do we get? So we get H2 of C2, C star, phi, which is the identity. And then we have some product with some cocycle, which I don't need to tell you what is, a little complicated, but it's an extension problem. It's like Stiefel-Whitney 1 times Stiefel-Whitney 1, it gives you Stiefel-Whitney 2. That's somehow what I mean. You have a space with Stiefel-Whitney 1, and then you multiply Stiefel-Whitney 1 of the other component, you get some Stiefel-Whitney 2 class. That's what is behind. But the thing is, we do this C2 cross Z2 homomorphism, and then times beta Z2. So what is all this? How many extensions do I have of C2? So the trivial and the non-trivial, which is t squared equals 1 and t squared equals minus 1. This is C2. How many homomorphisms do I have from Z2 to Z2? This is the gradient 2. And do I have a matrix algebra only, or a matrix algebra over the division ring, which is not just the complex number, but the complex numbers and a variable 2? And these products precisely make this into C4 and this into C8. And this is what he proved in the 60s. So namely, you actually get all these graded groups and you start getting information piece by piece. And then when you get the piece by piece, then you want to see whether what you get here, if you square it, then it lands here. And then you have this extension. And then you take a piece here and then you square it and it lands here. In Clifford algebras means here with the generator is the Clifford algebra 0, 1. Here you can think is the 0, 2. And here you could think is the 0, 4. This one square gives you this one square gives you this. This is the generator. So it goes all the way to Z8. But if I split it in pieces, I get this extension. So this was already done by CTC Wall, and it was exactly like this. So now we just added that we can have extra gradings and extra extensions. One of them is this SOC extension. So having said this, so what Tom was saying is these are the twistings. From topological point of view, one can actually get to the same thing, but it's a little complex because one has to use this Stifel-Vitti class. That one can do it. It's possible to do, of course. But from this perspective, it's a little simpler because we're not putting topology there. We're just actually doing algebra. Now, let me give you some sort of endpoint of this because we want to do some calculations. What is K-theory here? So this is a definition of Karoubi, again, 60s, 70s. Which is, of course, based on a definition of Atiyah, Bott, Shapiro. That is, how do you get the K-theory? Basically, you get the K-theory out of modules of these algebras in here. And then you just do a nice relation on them. And then you get the K-theory. So let me start with one of these elements. And this is a class in the graded Brauer G equivariant of the complex. So I have a class, which is all the structure that it entitles. First, what I can do is I can define something that I call APQ, which is simply you can always tensor it with the Clifford algebras. Because they are of this kind. It's like pulling them back. Because they are defined on Z2, you can pull them back to here, and then you can actually define an extra. Namely, there is a G here, but there is a Z2 here, and you can imagine that we just pull the information from this homomorphism to Z2. This algebra lives in here. We pull it back via pi. So it's like this. I would better call it pi pullback, the Clifford algebra. But let me just complicate this thing. With this in mind, then we can take modules of this algebra that are G equivariant. So we take G equivariant modules. So we take the category M of this gadget, divided. So this is isomorphism classes, if you want, of modules of this algebra that are G equivariant. So this is iso classes of these modules of this algebra that at the same time are G phi equivariant. What does this mean? This means that if I have a G acting on an element of the algebra that is multiplying a vector of the module, that means that this should be G of A times G of B. This is the definition. The way the algebra acts on the vector, then G, then it has to be the same as G acting on the algebra element, which later acts on the action of G of B. If we do this, the definition of the K-theory, it is by a beautiful idea of Atiyah, Bott, Shapiro, the paper modules. It is defined as the co-kernel. If I have these modules and I have A, I put here P, comma Q plus 1. Of course, there is a G, comma phi here. Then I just simply take the co-kernel of this map, and I'll tell you what is this co-kernel. Whatever the co-kernel is what I'm going to call the K-theory of the algebra over a point, equivariant. And what is this? If you have any module here, you have any module, I don't have theirs. You have any module of this algebra, it's automatically a module of this algebra because this algebra has less elements than this one. This is just the restriction function. And the idea of a Tijabot is if you are able to extend an algebra to an extra element, this extra element tells you the homotopy. These extra elements, an extra dimension that allows you to contract it to some trivial module. Therefore, if you contract trivial modules, you get these equivariant K-theory groups. Once you have this, then you can simply, of course, define that the total equivariant K-theory of a point of a magnetic group is the sum over the K-theories of representatives in the graded Brauer group. Graded Brauer group of the complement of G comma pi. G comma pi. Because this operation that I have here is basically acting by a C2 group on the group here, and it's actually cyclic, so it will come back. So this is what Karoubi said is the total K-theory of my magnetic group. He didn't call it like that because he was real at the time. But then we can see that the twistings are incorporated in the algebras. And of course, if we want, we can take the twistings and put it in the left side, but they're all incorporated in the algebras, and we don't have to somehow treat them differently or not. But the point was all this, and again, this has many things that I haven't resolved. As you can see, this is over a point, and nobody's doing anything with a point in topology, you know, in physics. So I need to scale it to tori and spaces, but you haven't scaled to them.
No, there are quantum dots.
Okay. Quantum dots in here, beautiful. But of course, because the next part has to be bring the topology, say the space, and the space also affects these objects. For you to know, one of the things that many things that made Grothendieck famous was a beautiful paper called the Brauer group of an algebraic variety. This Brauer group turned out to be a birational variety. This is a beautiful thing, which is generalizing this to algebraic varieties, to Asomaya algebras. And so this object is quite important also in algebraic geometry because it's to control the way you can have certain fiber spaces. This is some sort of the baby version of a point. Good. So to finish, because I need to give you I erased, but I shouldn't have erased anyway. Which is that the Eugenio yesterday told us that the K-theory is C4T with spinor recoupling is 4 periodic, not 8 periodic. The reason is simple if one looks at it this way. Of course, one can prove it several ways, but in this universe, it is actually simple. So what we have is Z2 here. This is my, with identity, this is my magnetic group. And here I have C4. So yesterday, Eugenio told us about the symmetries and the spinor recoupling. I will not explain that again. But these are my groups, and I put here my extensions. No, my extension was C2, C2, C star, C3, or identity star. I have some extension. I put a point, homomorphisms from Z2 to Z2, and then I have Z2. This part I never told you what it is, but this is, you forget about the grading and you simply get the graded Brauer group of the complex numbers.
We need to use another notation because the referee was complaining about the point.
Yeah, I need to change it. There are some complaints that should not pay attention. And so then there is other, then we do it for the C4, of course, magnetic with respect to the Mod2 map. We have homomorphism. And of course, this is categorically behaves well under pullbacks. So which pullbacks? Of course, there is a map here. That is simply mapping the first element to the first element, so the surjective map. And so what I want to see is what happens when I take all these Clifford algebras, whenever I have this symmetry, if I pull them back to C4, namely, give me the symmetries that you will have, which is these CPT symmetries that are there, but I want to pull them back to a bigger group, and I want to see what happens to them. So it's easy to see, of course, that in this part is an isomorphism. If you see the homomorphism goes, again, this is C2. There are only one homomorphism on trivial here. This is, again, an isomorphism. But here the point is interesting. This is C2. It's one extension, which is Z8 in some sense. And this is also C2. But this goes to 0. So what does this mean? This means many things. Of course, this means that this is a C4. And it tells me that the graded Brauer group of the C4 with respect, and I'll tell you why, with respect to the mod 2 map is not C8, it is C2, which is this one, central extensions, times C4. Already it's telling you it's not 8 periodic, it's C4 periodic, so it's smaller. But why is this happening? Because the time reversal that you took here, which we know in a nice model that lives there, we have our element that generates this, or the algebra that is generating this, which is, we like it so much, this matrix with complex conjugation that lives here, that generates this element. When you pull it back to this group, becomes a representation, a bona fide representation of C4. Because if you take this element and you take C4 and you map it to magnetic symmetries of Z2, then we just take 1 and we see that now the matrix is of degree 4. That means that the algebra that was done trivial here becomes trivial in the sense of Morita equivalence. So the object that here was not trivial and was generating this information, pull it back here, it trivializes because it becomes a representation. So it becomes 0. So because you see the order of this matrix is 4. It's not 2. But being 4, then these maps become 0. And of course, what it means is here we have the two options. Spin orbit coupling, which is this is off. The spin orbit coupling is this is on. So there are two options that he was saying yesterday. And this is the 4 periodicity. And in that sense, instead of calculating 8 K-theory groups, it's more difficult. You calculate 4 K-theory groups. So this is information to let you know, don't calculate that much because you're repeating your calculation. And in that sense, we were able to show these tables that he was showing yesterday. And let me finish with that, so I can tell you what some words about. Which is, we were, again, if you want to calculate K-theory groups, you need to calculate the whole spectrum, which is 8 periodic. So you need to calculate 8 homotopy groups and then carry on. But if you know that there are only 4, beautiful, and you have to half the work. So that's why I was half the work for myself. So the point is, this was shown by Eugenio yesterday. So this is all magnetic. Again, this is again mod C2. No, I'm not going to write it, but mod 2. Now the tori, and so we have dimension 0, -1, -2, -3, periodic. So you can imagine this doesn't really matter. So this is C4, that's C to the 4, Z2, Z2 plus Z2, and then 0. And if we twist it, but the twisting here, this is again 4 standing for those C4 there. This is the C4 that is on the right-hand side. And here it stands for the Z2, which is the twisting. So here I put Z8 as Eugenio was saying yesterday. This is the other twist. And the groups are curiously so the same ones but shifted. So Z2 plus Z2, 0, C4, and Z2. Now, of course, if you have the answer, you could have forgotten all about this. But to make the answer, I have to go through all this calculation. So here is the class, of course, that we were talking about yesterday. Of course, there is another class, but this is a topological quantum chemistry class. It's a way how you build the bands without caring about the Chern class. There are many ways to build the bands. I think it's topological quantum chemistry, as they are called. You just know what happens on the points of high symmetry, and you just see how to glue them. This is there are two options to do that, and this is the one that is coming from the bulk. But why is this important? Why do I care in some sense, by other means? What is going on here, there is something that is called T-duality. Or is written as T-duality, which is something that you start in T2, like space, and something that you have T2, momentum. Let me put it with a hat. And your information in space you pull it back here, where you can couple it with the momentum, with something called the Poincare line bundle. So you take an element here, you put it back here, you do some object, and you push it down. So usually you take an object, you pull it back to here, you couple it with some line bundle, and you push it down. So you go from the K theory here to the K theory here, but this pushing out is not easy to do in K theory because you need to know what is the orientation class. So it turns out that the spin orbit coupling here is precisely the orientation class that allows you to do this pull down. So you cannot avoid having the twists because the twist is exactly the obstructions of the orientability. So if you want to push down something that is non-orientable, and you might think, but what is non-orientable here? Because all these spaces are orientable, but the group action is non-orientable because the group is a subgroup of SO3. So you need to lift it to SU2, and that's the problem, and that's the spin orbit coupling constant that has to go down here to be able to do this push forward. So to finish, I've been asked by people here, oh, you are going to tell us about the Kitaev table of all groups. I was not thinking about that, but I'm glad that everybody read my abstract and thought I was going to do that, so I could get the attention of everybody. Because this is just the first step. Because if the question is, give me the Kitaev table for all magnetic groups, or, well, I need to carry out these calculations for all possible magnetic groups. Hopefully it's easy, but I don't have it easy so far. I just did one calculation. And the calculation I did was not easy. I had to do it by hand. Maybe there is some sophisticated way to do it in a computer, but we have to do it by hand. Extension problems and that. And so to do this for how many thousand magnetic groups there is in the system, so I cannot do it. But the point is that at least the structural information is organized. I'm organizing the structural information. Of course, nothing here includes translations. As Professor Terry was saying yesterday, okay, there are 8 classes of Clifford algebras, 2 classes of complex numbers, there are 10, but there are other ones. Well, these other ones only arise when you couple translation with time reversal. They don't arise. And why? Because these partial translations is you move half the lattice and you do complex conjugation. This is not included here, and that's difficult to calculate. But the T-duality map allows you to put it in another perspective, which is easier to calculate using the torus. And that's right, it comes the self-conjugate K theory, which is difficult to calculate. It has a spectrum of 4, so there are 4 more, but that's only when the translation is actually only moving in the X. But if the translation is half X, half Y, half Z, another thing. It's not the same as that one. So that's only when the half translation is in one axis. But then we have to couple with more half translation with rotations, and then because the question is how to classify all possible representations of all possible groups with all possible K. I don't think I can do it myself, but maybe for your device. So if you go home with something, is that there is this great Brauer group that encodes all the twistings that Tom was saying in a somehow compatible way, which basically is telling you the algebras that are behind are controlled by this object, in the sense that if you tensor with endomorphisms, the topology doesn't change. It's like adding bands without information. They don't do anything topologically. And then if I know this, which is not difficult to calculate, where you can actually do it, then you know exactly how many twistings there are, or how many possible combinations of operators you may have. The algebra. I'm not giving you the representation or even the Hamiltonian. This is the first step. What is the algebra? I have T, C, T is square 1, T square minus 1. So thank you very much for your attention.